2021 APWA Colorado Construction Inspectors Conference. On behalf of the Colorado chapter of APWA, American Public Works, I want to welcome you all. I'm Mike Martin, the 2021 Colorado chapter president for APWA. APWA, we've transitioned to these online virtual conferences, and the organization and our chapter is still committed to providing you and your team valuable resources, training, and access to all the cutting edge products and services needed in our industry. So thank you for your time and your interest in coming in today. This is really important that we continue to do this. Thanks for joining. Like I said, we've got 4 wonderful speakers today. Excited to hear the topics. The session again is being offered as part of that conference that we typically would be getting together in January, and hopefully we will next year. But we'll have 3 sessions. This is the first of 3, so hopefully you can attend all those. I want to know we did do some sessions towards the end of last year that are posted online, one on 5G small cells and one on being effective virtual speakers, virtual communicators. So those have been posted online. If you're interested, you can go and check those out. I do want to acknowledge our sponsors for today, and a huge thank you to them. They're very important to having us hold these meetings together. So I want to acknowledge them. I've got Colorado Ready Mix Concrete Association, the American Concrete Pavement Association, Cutler Repaving, and Colorado Barricade. So thank you very much to our sponsors. We appreciate that very much. So a couple housekeeping items before we get going. This session is going to be recorded, so just making you aware of that. So afterwards, we will post this recording to the website so you can see it after the fact. Initially, everybody will be muted. So I just want to let you know that. So you're going to be muted. When we get to the Q&A session later, you can be called upon if we need to bring anybody else in. As a general item, we're going to hold all the questions to the end. So we're going to have all of our speakers speak, and then we're going to have questions at the end. If you want to submit a question, if you see down at the bottom center of your window, there is a chat area and a Q&A area. Submit your questions there. We will then be monitoring them, and we will bring them up at the end of the session if time allows. So just that's the way to get questions in. And then lastly, just there are no CEU credits for today. We're not going to go through that process. So that's just wanted to make everybody aware of that. So with no further ado, I will turn it over to Angela to introduce our first speaker. Thank you.
All right, thanks so much, Mike. I'm Angela Folkestad. I'm Executive Director of the Colorado-Wyoming chapter of the American Concrete Pavement Association, and we're super excited to have helped coordinate the speakers for today's session, focusing on corrosion and steel corrosion in concrete, and trying to offer some ideas of how we prevent it, how we identify it, and just kind of a whole host of information around this topic. So while we're disappointed we can't see you all in person, we're happy to be able to bring in some speakers around the country that maybe we wouldn't have been able to do without having this virtual setting. So great opportunity for you to hear from some people that you might not normally hear from. So the first presenter we have today is Dr. Charles Mai, and he is head of engineering in the Admixture Systems Division of Master Builders Solutions, and he's based in Cleveland, Ohio. He's been with the company since 1987, and he provides technical leadership and strategic guidance in the marketing of admixtures and high-performance concrete technologies. Dr. Mai is a fellow of ACI, the American Concrete Institute, and is serving a 2-year term as vice president of the Institute. In 2013, he was awarded the ACI Arthur R. Anderson Medal for outstanding contributions to the advancement of knowledge of concrete as a construction material in the areas of corrosion and chemical admixtures. So he is the right person to have talk to us today about all of the steel corrosion issues. So welcome to Charles.
Thank you, Angela. And good morning to everyone. It's a pleasure to be part of on the panel today to bring you this topic. And since I cannot be with you in person, I am, just so you know, over the clouds in Cleveland, Ohio. So over the next half hour, I'm going to be talking about concrete reinforcement preventing corrosion. And specifically, this is what I'll be covering. I'll give a brief overview of corrosion of steel reinforcement, how to prevent corrosion in new construction, repairing corrosion in existing structures, And then also at the end, I'll present some resources that you would find valuable. And since we're talking about, with respect to inspection, I will point out as I go through things that you should be cognizant of. So how big a problem is corrosion? Now, this quote actually comes from a publication that dates back to August 2000. So we're talking about over 20 years ago, but it's pretty much on point. And in this particular publication from the Federal Highway Administration, it was estimated back then, that the cost of repairing and replacing bridge decks, corroded bridge decks, was approximately 20 billion and increasing. And I do know that it is much, much more than that. So corrosion is a big problem, as I'm sure you're all very much aware of. Now, so just a brief overview of the corrosion of steel. And don't worry about the chemical equations over here. I'm not a chemist, I'm an engineer. I'm not going to go through them. But one of the things that we're all aware of is the fact that concrete is an alkaline material. It has a high pH. And it turns out that this high alkalinity of concrete, the high pH, is actually very good, so far as steel is concerned, because it helps in the formation of a natural protective oxide layer on the surface of the steel, which we call the passive layer. And as a result of that, concrete typically will prevent steel from corroding. And there are a lot of reinforced concrete structures out there that are not corroding. So that's testament to the fact that concrete is able to protect steel from corroding. So the question then becomes, why does corrosion occur? Well, corrosion occurs if the passive oxide layer or the passive layer is disrupted. And it can be disrupted as a result of chlorides getting to the surface of the steel, or a reduction in the alkalinity or the pH of the concrete, and this is normally through a process called carbonation of the concrete, where atmospheric carbon dioxide diffuses into the concrete and reacts with it to change some of the byproducts of the hydration process. We can also get corrosion occurring as a result of contact with dissimilar materials. So let's say if you have just your normal reinforcing steel in contact with aluminum or some other type of material, that would constitute dissimilar materials, and that can also cause corrosion. Now, in order for corrosion to occur, the things that we need to have moisture, so that's water and oxygen, and then there's got to be a breakdown of the passive oxide layer, as I said earlier. Now, where do the chlorides come from? The biggest source of corrosion is chlorides. And these chlorides come from de-icing salts that we use in the wintertime for snow and ice removal. They can also come from the groundwater, from brackish water. A lot of chlorides also definitely from seawater and airborne chlorides, for structures that are located along the coastlines. And also chlorides can come from the mixture ingredients, and specifically calcium chloride, if it's used in making the concrete, or admixtures that contain calcium chloride. In some places, people use marine sand for making concrete, and you can also get chlorides from from the marine sand in those applications. Now, the issue with chlorides is once they get into the concrete and they accumulate in sufficient quantity at the surface of the reinforcing steel, they cause corrosion to occur. And when corrosion occurs, we have byproducts of that are formed, and we typically call that rust. Now, if we think of the iron as having one volume, the rust products that are formed, which are oxides of the iron, as you can see from the schematic on the right, basically occupy a volume that is greater than the original volume of steel. And as a result of that, what we end up having is an expansion within the concrete, which then leads to cracking and spalling of the concrete cover. And then, of course, once that happens, we begin to see the rusted reinforcements, and it progresses quite rapidly. Now, corrosion tends to is an electrochemical process, which means that in the laboratory, we're able to actually measure the amount of current that's generated. You know, when the corrosion process starts, you end up setting up a cell, which is similar to your battery in your car. So we're able to simulate that in the laboratory. And the things that are critical are the time to corrosion initiation. And typically this occurs when we have sufficient chlorides at the surface of the steel. And then the question then is, what is the magnitude of corrosion that occurs over time? You know, and that gives us an idea as to the severity of corrosion that's occurring. Now, out in the field, how is it manifested? Now, these are some very severe cases. This was a bridge deck in Cleveland that was badly corroded, and well, we didn't tear it down; it got fixed. Here are other examples of corrosion. You know, the picture on the left is from a parking garage. Then obviously the one in the middle is in a marine environment. The picture on the right is also from the marine environment down off the coast of Florida. You know, and then again, just the immense destruction that corrosion of steel can cause. So now let's take a look at the options that we have for protecting steel reinforcement in concrete from corroding. And what I've done is I've listed them under 5 different categories, and you see in a minute why I've done so. But we have surface barrier systems, we have steel surface protection systems, we can use corrosion resistant concrete, we can also have alternate reinforcing systems, and then we can use cathodic protection. Now, cathodic protection is a system whereby we provide a sacrificial anode. Typically, these are zinc-based, and though they tend to be electrically connected to the reinforcing steel, such that it's the zinc anode that corrodes instead of the steel. So this way, we protect the steel from corroding. So that's why we call them sacrificial anodes, and that's cathodic protection. And I wouldn't be saying too much about that in the rest of the presentation. Now, starting off with, before I get into it, all of these systems that I've talked about, as you can see, are basically different, and as a result of that, they have different degrees of effectiveness. They offer different protection mechanisms. And as you can imagine, they will offer varying costs, both initial construction as well as with repairs over the life of the structure. And as a result of that, typically, the only way to determine which system is better or is the best to use will be by going through a life cycle cost analysis. And this is something that the designer engineer or the repair engineer will do and then specify which option to go with. Now, let's start off with the surface barrier systems. Now, these are either, as you can see here, membranes or penetrating sealers, and these are applied at the surface of the concrete. And the whole objective is to make it difficult for the chlorides to penetrate into the concrete. And if it's done effectively, essentially, you will have a very slow ingress of chlorides into the concrete. Now, these systems have a life to them. So membranes typically will have to be replaced after X number of years. And same thing with penetrating sealers. They would have to be replaced after, let's say, 3 to 5 years. But these are intended to prevent chlorides from getting into the concrete. Now, next, if The next thing that can be done will be to use concrete that has low permeability. And there's several ways in which low permeability can be achieved. One will be by reducing the water, total water content that's used in making the concrete. And by so doing, reducing what we call the water to cement ratio of the concrete. We can also reduce the permeability of the concrete by using supplementary cementitious materials. So in addition to Portland cement, adding things such as silica fume, fly ash, slag cement, metakaolin, or some other types of materials. Now, there are also some chemical admixtures that can be used that help in reducing the permeability of the concrete, such as styrene butadiene latex. Now, the benefits of reducing the water-cement ratio is that, as you can see from this graphs, the coefficient of permeability of concrete, as shown here, decreases very rapidly as we go down in water-cement ratio. And typically, for structures that will be exposed to corrosion, the maximum water-cement ratio is going to be around a 0.42 or so. So we're going to be down in this range where we have low permeability. Now, why is this important? From an inspection perspective, it's critical that the total water content of the concrete is not abused, that we don't have indiscriminate additions of water to the concrete, either at the batch plant or when it gets to the job site. Now, with respect to, as I said earlier, supplementary cementitious materials can provide very low permeability. And it turns out that sometimes when we combine them, we actually get much, much better results. So the graph on the left-hand side shows the ingress of chlorides into concrete made with Portland cement, as shown here, fly ash, silica fume, and then here you have a combination of silica fume and fly ash, and you can see that it yields significant benefits. And from a modeling perspective, as shown on the right, the combination of the fly ash and the silica fume, as you can see, gives us the lowest ingress of chlorides. And my favorite way of reducing corrosion is to use a combination of supplementary cementitious materials. Now, the next thing that can be done will be to actually provide protection at the surface of the steel. And typically, that is done by using steel surface protection systems, such as epoxy coating or zinc-coated reinforcement and so on. And so in this particular situation, we have chlorides getting into the concrete, but when they get to the surface of the steel, because of the barrier, you need to accumulate a whole lot of chlorides before corrosion can even initiate. So that's the benefit of these systems. Now, what does this mean? If you are the job site and they're using epoxy coated reinforcement or any bar that is coated, if the areas that are damaged, the damaged areas would have to be repaired before the concrete is placed. The next thing that we can do would be to use corrosion-resistant concrete. Now, corrosion-resistant concrete will be concrete that contains corrosion-inhibiting admixtures. And there are two different types of admixtures in the marketplace. One is based on calcium nitrite, and the other ones are based on their organic polymers, their organic-based systems. Now, these materials also work at the surface of the steel by increasing the chloride threshold for corrosion initiation. That is how much chloride we would need, how much salt we would need at the surface to break down the protection that they provide and thereby cause corrosion. So in a way, again, increasing somewhat similar to what epoxy does, but through the use of integral corrosion inhibiting admixtures. The things that I just want to point out, if they're using calcium nitrite tends to accelerate the time of set of concrete. So typically we will add a retardant admixture to the concrete to control it. but this is something that you need to be aware of. And the benefits of using corrosion inhibiting admixtures as shown here is that they delay the time to corrosion initiation, and the duration by which they can delay it depends on the amount of corrosion inhibitor that's actually used in the system. And as you can see here, by delaying the time to corrosion initiation, they also delay the total corrosion that can occur. And if done properly, you can have a situation where over the life of the concrete, there will be no need for any repairs at all, or just very minimal repair. Now, the last system that I'm going to be talking about will be now the use of alternate reinforcing systems. So this will be stainless steel or non-metallic reinforcement, or what we call fiber reinforced polymer bars. Now, stainless steel has a very high threshold for chloride. So essentially, over the life of the structure, it will not corrode. Non-metallic reinforcement, the FRP bars, basically are non-metallic. They're polymers, organic polymers. They're made from organic polymers. So there's nothing to corrode. Now, these systems are available. They're very expensive, especially stainless steel. With non-metallic reinforcement, the FRP bars, they cannot be bent. You cannot bend them, and so they do have some limitations. But these are the systems that are available for preventing corrosion of steel with respect to new construction. Now, there are some other factors that we need to consider, when it comes to assuring the durability of concrete. And these include having proper design, which is a responsibility of the design engineer, detailing, concrete cover, as well as having detailed specifications and approval of the appropriate concrete materials. The production of good quality concrete becomes very important. And then following best construction practices and having well-executed quality assurance plans and proper maintenance. And then obviously, when it's all said and done, everything can be short-circuited if the concrete cracks. So we need to prevent that. Now, I talked about concrete cover over the reinforcement. And if the design can permit it, it makes perfect sense to increase the concrete cover because it basically increases the depth of concrete that the chloride ions will need to go through in order to get to the surface of the steel. And this is one of the recommendations in ACI 362.1R, which is the guide for concrete packing structures. And they do acknowledge in this particular guide the benefits of using increased concrete cover. Now, I talked about production of good quality concrete. Now, this was a video that I took at a concrete batch plant. And the question, if you're watching this, is how much water actually went in on the slump rack? And where is that accounted for on the batch ticket? So again, these are things, little things that can happen when we're talking about corrosion or shrinkage of concrete and so on. The total water content becomes critical. So indiscriminate additions of water can have an effect. In terms of good construction practices, at the job site is a concrete cover over the reinforcement as specified, because a decrease in the concrete cover can shorten the corrosion service life of the structure. Things such as minimizing delays is a contractor prepared at the job site. Is a concrete at the when it gets to the job site, does it have the right slump and the air content to be placed so we don't end up in a situation where it's rejected? And then in terms of the placement of the concrete, is that appropriate? Can the concrete be consolidated and finished properly? And then once all of that is done, what about curing of the concrete? The concrete needs to be cured properly. And sometimes curing protection will be required for the concrete before the final finish, and also before final cure is applied. So talking about placing concrete. Are you ready to place and vibrate concrete in a structure like this that has this much congested reinforcement? This is a photograph from a project in Nevada, where after 3 concrete tracks, they realized that there was something seriously wrong. That's the photograph on the left-hand side. And they stopped placing concrete strip forms and then realized that the concrete just was not getting down and being vibrated properly. The photograph on the right-hand side is was supposed to be a liquid containment structure. Now, how can you have a liquid containment structure when the concrete is honeycombed, as shown here? And even before the construction was finished, they had to jackhammer this whole section and essentially replace the concrete. These are other types of things out there where the placement was not adequate. These are drill shafts, where the concrete basically did not go through the cages, and that causes a problem. What I'm trying to get at is the concrete needs to have the right level of workability and fluidity in order to be placed and consolidated properly. So how about having the concrete do the work sometimes, if feasible? Now, these are things that the design engineer will typically be concerned about. In this particular situation, the concrete that's being used is self-consolidating concrete, which is able to flow through the reinforcement into the formwork and requires very minimal vibration for consolidation. So all of these things are there. Now, I talked about cracking, and cracking can short circuit anything that we try to do with respect to the corrosion of, to protect steel from corrosion. And several years ago, Caltrans out in California, did a study where they had a bridge deck, as shown on the left-hand side, the photograph on the left-hand side, using their typical concrete mix. And then on the adjacent side, they added they added a shrinkage reducing admixture to it. 9 months later, they inspected the bridges. And as you can see on the left-hand side, with the regular concrete, they ended up with a lot of full depth cracks that had already started leaking. And obviously, if you have chlorides in this particular situation, the chlorides will get down into the deck, into the concrete. On the right-hand side with the SRA, there were no cracks whatsoever. And as a result of that, Caltrans basically implemented their crack-free bridge deck program, which uses shrinkage reducing admixtures as well as fiber reinforcement. And they did an in-depth study where they've shown that the crack-free bridge deck concrete that they're using essentially would save them millions of dollars over the years in terms of reducing their maintenance cost. So this is available. Now I'm going to finish off by just talking a little bit about concrete restoration and repair. And there are various reasons why concrete deteriorates. And one of them, as you can see, is the corrosion of reinforcement. And as a result of the deterioration of concrete, we normally end up getting cracking, spalling, and delamination, loss of concrete section, as well as loss of steel area, which then results in an overall loss of structural integrity. Now, what this means then is that the concrete would have to be repaired in order to protect the reinforcing steel. So we'll take a look at this process. Now, ideally, as shown on the left-hand side, what we want to do will be to have a completely monolithic replacement. Now, obviously in repair, that's not quite feasible, but the benefits of having a completely monolithic replacement is that you end up with the same physical properties and you have a high degree of durability and protection. But a lot of times what we end up with is partial depth repair with some repair material. And things that we need to be concerned about then will be material compatibility, bond to the substrate, as well as the effects of shrinkage and cracking, and what we call the ring effect. And the ring effect will be when the corrosion moves from the area that was repaired to the adjacent sections that was actually repaired. Now, the repair process itself would involve a condition assessment to determine the repair area, demolition of the section to be repaired, as well as preparation of the surface, and then finally application of the repair material, and then curing. The basic steps involve removing surface contamination, edge conditioning, the ball concrete. If there are pieces of steel that are badly corroded, they may have to be replaced, lapped. And then we need to clean the concrete and the steel surfaces, apply bond coats as needed in order to place the concrete. And these are the various steps that would typically be involved. In terms of edge conditioning, we normally would want to have square cut edges with a concrete saw about 1/2 inch or less in depth, because what you want to avoid will be feather edges. And the patches need to be square or rectangular in shape. The ball concrete removal, different processes that exist for doing so: chipping hammer, hydro demolition, scab shot blasting, sandblasting, or acid etching. And if you're not aware of it, they're the concrete surface profile chips, the CSPs, that you can get from the International Concrete Repair Institute. Undercutting the reinforcement. If the reinforcement is corroded, you want to make sure you undercut the reinforcement to expose the corroded rebar so it can be cleaned properly. Repair surface geometry. So if you do a survey and this is what is found in terms of the delaminated or cracked area, you want to make sure you have the proper layout. And as shown on the right-hand side, that will be the proper way to do it, instead of having a patchwork of sections that are taken out. Because as you can see here, this can result in cracks at the areas where you have the reentrant corners. The process itself, again, once the cavity has been cleaned, will be to clean the reinforcement, also clean the surface of the concrete, pre-damping the surface, and then apply a bond coat. Now, typically when you're working with a repair material, the best thing to do is to follow the manufacturer's recommendations in terms of how to apply the material itself. And one of the benefits of the surface cleaning and the pre-dampening is the fact that it helps to open up the pores of the concrete, and that then enhances bond between the substrates and the repair material that is applied. So just to finish off, in terms of resources, you can get a lot of material from the International Concrete Repair Institute. We refer to that as ICRI, and I've provided the link to their bookstore here, as well as also from the American Concrete Institute. We do have a repair code, ACI 562, that was released a couple of years ago, and typically that's what the repair engineer would use to formulate a game plan with respect to repairs. But for inspection purposes, the documents that you have at from ICRI will provide a lot of guidance. So if you're not familiar with them, hopefully this gives you a chance to become to know what they are. So with that, I'd like to say thank you very much, and I'll be staying on, and I believe we'll take questions at the end. Thank you for your time.
Thank you, Charles. We really appreciate you taking the time to join us today and run through all those different scenarios. And
Angela, I
provide some
think you're
additional-
muted.
Can you hear me now?
Yes. we can.
Okay, perfect. So thank you, Charles. We really appreciate you taking the time to join us and explain all these, all the different concepts and what we can do to prevent and fix some of those steel corrosion issues. So you kind of, introduced some of the concrete properties that are important and that we can incorporate into helping to prevent steel corrosion. And so we're going to have Sarah Sanders with ACPA talk a little bit more about how those apply specifically in Colorado and some of the specs that are out there to help us with that. So Sarah is a lifelong Colorado resident. She holds a Bachelor of Science degree in civil engineering from the University of Colorado at Boulder. And she started her career with a concrete paving contractor and progressed to lead their quality control department. Sarah also worked for a consultant as a concrete special inspector before joining ACPA. In addition to providing technical assistance related to concrete pavement design, construction, and rehabilitation, Sarah manages the CDOT ACPA Concrete Pavement Inspector Certification Program. She's a registered professional engineer in both Colorado and Nevada. So welcome, Sarah.
Thanks, Angela. So like Angela just said, I'm just going to run through real quick some of the specifications that we have here in Colorado to address these topics. You'll see it's a lot of the same topics that Charles just discussed. So I'm just going to go through how we have implemented them. So historically, because concrete's been around forever, we've accepted, designed, and specified all of our concrete, not just pavements, based on three main things, which are strength, slump, and air. We've always had these thought processes that more cement leads to more strength, and really all we cared about was strength. But through research and new testing and some new programs we've found out that there's some more important factors in this, and these thought processes just generally aren't true. So as we go through and write these new specs, we need to look at what actually matters in our concrete. And you'll see one of the main factors there is going to be permeability. And that's where the main one we're going to talk about today. We do have all of these other factors that we all definitely want to be paying attention to. But as far as corrosion, that permeability is going to be what we're going to focus on. So CDOT's new 601 specification, if anybody doesn't know, in the CDOT spec book, section 601 is where you find all of the concrete mix design information for both structural, concrete, pavement, really any type of concrete that you're going to deal with. So this came out in October of 2019, so it's still fairly new, but we have made it through one construction season with this spec. And with this, the main goal was to move towards performance engineered specifications. So you'll see as we go through this, we're focusing more on end results and getting that permeability and the durability factors that we want in the concrete instead of just focusing on strength like we used to. Now that this spec, now that CDOT has put this spec into use, we are seeing some local agencies start to implement similar specs, and we're expecting in the next couple years to see these specs start trickling down into other applications. So hopefully everyone knows the basic components of concrete, right? We're going to have our air, cement, water, and multiple sizes of aggregates generally. So how do we control all of these different elements to control our corrosion? So the first one we're going to look at is cement content. So with our old strength requirements, we used to see a lot of over design in the concrete and using more cement than was actually needed. And doing this really affects the permeability, the shrinkage, and also the cost of the concrete. Because permeability is going to be directly related to the paste content in the mix with the cement content. So you'll see in these new CDOT specs, there is no minimum or maximum cement content specified. It is up to the contractor and the mix design lab how they want to design the mix and how much cement they actually need to use. And so with that, we're going to use the supplementary cementitious materials like Charles talked about. So we have a few different ones available in Colorado. Class C fly ash, Class F fly ash is going to be our most common one. We are starting to see the Class N come into the market and be used here in Colorado. And you'll see on the right there a list of why we use these SCMs and why we specify them. And you'll see those first two there, again, reducing that cement paste and decreasing the permeability. So we do require 20% replacement of cement with SCMs in all pavement mixes in CDOT, and they're not necessarily required in the other classes of concrete for structural use, but they are allowed and can sometimes be specified for other reasons besides corrosion, like ASR mitigation or a few other things. And one thing to make sure when we're using these SCMs is we're replacing that 20% of the cement. We're not adding the Class F fly ash to the cement that we already have in the mix. We're also going to use optimized aggregate gradations. We have many contractors that have been doing this for a number of years. So instead of like we used to do standard gap graded mixes where you had just one coarse aggregate and one fine aggregate, we'll now start using 3 or 4 different sizes of aggregates and adding bins at the plant. And this has a lot of benefits to the mix and to the concrete. Again, it's going to reduce permeability, cracking, and CDOT and most local agencies do allow and even encourage these optimized gradations. And then the other factor is that water to cementitious ratio. So we always refer to concrete as a hard sponge. So what that means is the more water that's in it, the more porous of a sponge it is. That leads to more separation between the cement particles, which reduces strength and increases that permeability. So most of our specs here in Colorado are going to specify a maximum water cementitious ratio of 0.44 or 0.45, depending on the type of concrete and the spec you're looking at. You'll see in these new CDOT specs, we do not specify min or max water cementitious ratios. Again, we're trying to get the contractor to figure out what works. And as long as they meet their permeability requirements and shrinkage requirements, it's up to them to set what the water cementitious ratio is. So in the end, all of these materials are going to work together to reduce that permeability. So I think this graphic represents it very well. If you look at, as you move from left to right and you add in different sizes of aggregates to get to that optimized or well-graded gradation that you see there on the right, if you look down below, those gray boxes indicates the paste content that's going to be in the mix with that gradation. So if we can optimize our gradation, limit that paste content through a reduction of cement, as well as replacing a portion of it with the supplemental cementitious materials, that's going to get us that durable mix that we really want to see. Also with these new specs, we do require testing for permeability. This is required for almost all classes in the CDOT spec. So whether it's structural, bridge, pavement, what have you, there's 2 different options in there that the lab can choose from. So the rapid chloride permeability test and surface resistivity. Both are good tests. We'll learn more about those here in just a couple minutes. So I'm not really going to go in depth, but this is a requirement for our mix designs. And then there's also admixtures. So when we get into the use of accelerators, we want to make sure that they do not contain chlorides. So most specs will specifically state that calcium chloride is not allowed. And then corrosion inhibitors are also used in certain instances. There's a whole list of them that are approved on the C.APL. And then finally, so the mix is our first line of defense to keep all these corrosive materials and the chlorides in the water out of the concrete and away from the steel. But if it does get in, we do require epoxy coating of all reinforcement that's going to be exposed to these materials. So you'll see in any pavements, a lot of the structural work, that epoxy coatings are always required. And with that, I think we'll turn it over to, well, we'll have Angela introduce our next speaker. So thanks for having me.
Thank you, Sarah. I appreciate you talking through all the local requirements. And just to kind of take it one step further with the discussion on the testing, we have Jagan Gudametla to help explain some of those test procedures in a little more detail. And so Jagan currently works as the project manager for the FHWA's Mobile Concrete Technology Center, MCTC. We'll use that from now on. He has been working as a consultant for the FHWA since 2003. Jagan received his master's degree in pavements and materials from Auburn University. He's a registered professional civil engineer in Virginia, Maryland, and California. And we were excited to welcome him in 2018 to spend some time in Colorado with the mobile concrete trailer. You may have seen it down at C470 in Wadsworth. It was out there for a few months. So Jagan's going to tell us a little bit more about what he does with the trailer and also the testing. So thank you, Jagan.
Thank you, Angela. Well, first of all, good afternoon, everyone. Thank you all for the opportunity. So before I begin my presentation, let me put in a shameless plug on our Mobile Concrete Technology Center. I would imagine that a lot of the audience today may not be familiar with our program. So, just want to put in a slide and talk about the trailer a little bit. Basically, we are a technology transfer vehicle. The trailer belongs to Federal Highways, and we go across the country demonstrating new technologies that are practical and field implementable. And we go to all 50 states. The one thing I would specifically kind of mention today is we do have an equipment loan program. So most of the equipment that we have on the trailer, we have multiple pieces of it. If an agency or a contractor is interested in a certain piece of equipment, they are more than welcome to borrow it from us and use it. So the idea is that, rather than an agency spending, a bunch of money on a piece of equipment that may or may not work for them, this way they could try it out and hopefully, if it works for them, they would then eventually go and implement it in their specs or maybe purchase it on their own. We also offer a training on a lot of this equipment and these technologies, and we also participate in conferences and workshops. And I just kind of want to mention this just because, like I said, majority of the audience, at least for this audience, may not be familiar with what we do. And all the services that we offer are free. So please take advantage of it, especially, typically we travel a lot, and the last year we haven't really traveled a whole lot because of COVID. So we are offering a lot of virtual sessions, and so I'll be talking today on measurement of the permeability of concrete. So some of these tests, if these interest you, you're more than welcome to contact us at a later time. If you have any questions as you are using this equipment or something else. So with that said, well, what is permeability? Well, permeability is the ease with which fluids can penetrate within the concrete. As Charles had mentioned, you can have chloride ions go through, you could have all kinds of other bad actors that could go through and eventually cause corrosion. Now, if there's only one test that I would measure on concrete, then that would be permeability, because I believe that permeability is like a fundamental property in the sense that if you have concrete that's really dense and that doesn't really allow a lot of these bad actors to get through concrete, you're going to have concrete that's going to last a really long time. Not just in terms of corrosion resistance, but it could be, a lot of other durability aspects as well. So how do we lower permeability? Charles did a great job of going through a list of different things that we could do, including lowering the water cementitious ratio, using supplementary cementitious materials, minimizing paste volume. Now, this is something that we historically haven't really done a great job with, because at the end of the day, it's not the aggregates that contribute to permeability of the concrete, it's the paste. So if we can somehow minimize the paste volume, as Sarah had shown in some of her slides, it'll really benefit us with lowering our permeability. So of course, we should also be focusing on curing and also making sure that there's no cracking. So from a permeability standpoint, I mean, these are the things that we could do to reduce permeability of the concrete itself. But how do we measure it? I mean, and that's going to be the topic that I'll be talking about today. So historically, we have this test called the rapid chloride penetrability test. It's almost 40 years since it became a standard. It's a very common test used across the country. Basically, it's a surrogate measure of a surrogate way of measuring permeability. There is an ASHTO test method associated with it. As Sarah had mentioned, this is in Colorado specifications at this point. So in terms of performing the test, it is quite labor intensive. Basically, what we do is we take a 4x cylinder, we cut it into 2-inch sections, and then epoxy the 2-inch sections, the slices. And that's what we do in the first day. And then the second day, we take these sections and put them in a desiccator and vacuum saturate the specimens. And then on the third day, we put the specimen in between two solutions and kind of create a battery and basically measure for a certain time period how many ions, chloride ions, would go from one end of the specimen to the other end of the specimens. So if you have higher number of specimens go, or higher number of chloride ions go to the specimen, that means that that particular concrete has higher permeability. So as I said, this test has been there for a really long time, and it's been extensively used across the country, but it's not used as much or as frequently as it should be, just even though permeability is such an important property. And the reason for that is the labor intensive nature of this test. As I just showed you here in this slide, I mean, it takes literally 3 days to run a test from end to end. So now we have a brand new test, which we are extremely excited about. This test is called the surface resistivity test. Basically, it gives us similar information as a rapid chloride penetrability test, except this test literally takes a couple of minutes to run this test versus the 2.5 days or 3 days that it typically takes to run the rapid chloride penetrability test. It is a non-destructive test, and it's, you don't need to use any chemicals or anything like that. And because it's non-destructive test, the typical rapid chloride test, the test would be run at 56 days. But with this particular, testing apparatus, we could actually start running the test, as soon as we want. I mean, as soon as literally we remove the molds, the specimen from the mold, we can start running the test. So if you're looking for a certain number, you don't need to wait for 56 days. I think in Colorado, the number that we're looking for is, I think, 12 kilo ohms based on Sarah's spreadsheet. So if you're looking for 12 kilo ohms, we can, maybe receive, this concrete may have obtained the 12 kilo ohm or reach the 12 kilo ohm resistivity by the time it's only 28 days. So that's one big advantage with this. And there is an ASHTO test method associated with this test. So the way the test works, it has 4 probes on it, and basically the outer probes measure the current or apply current, and then the inner probes measure the voltage. And based on Ohm's law, we can then calculate resistance, and then from resistance, we can calculate resistivity, which basically correlates to permeability. So the higher the resistivity, lower is the permeability. Now, as I said, there are many advantages of this test. It's significantly faster. I mean, the cost associated with running the test is many magnitudes lower than the traditional rapid chloride test. No sample preparation involved. Again, I cannot emphasize this enough. I think this is one of the reasons that the rapid chloride test was not done historically, a lot during actual production of concrete itself. It's typically done once during mixed design submittal and maybe a few times during actual production itself. But because this test is so easy to run, now we have the advantage of using this test or running this test on specimens on a daily basis. And like I said, it's non-destructive. So you don't need to make extra specimens. The same specimens that you cast for strain cylinders can also be used to run the resistivity testing. No chemicals involved. And the other ironic thing is the cost of the equipment for this is, I think, like 6 times cheaper than the rapid chloride test. I would say maybe between 4 to 6 times cheaper. So here is the data from the 2 different tests. This is data from Florida DOT. So on the x-axis, you have the traditional, the historical test, the rapid chloride penetrability test. On the y-axis, you have the surface resistivity data. So what you would notice is the correlation is, in this case, it's over 0.94. And so it's excellent. I mean, the number, the correlation is really good. But the one thing to keep in mind is that the scales are different. So for rapid chloride, in this case, the scale is from 100 to 100,000. And then on the y-axis, you have surface resistivity. The numbers range from 1 to 100. So essentially, we're measuring, even though the correlation is really good, you're measuring 2 different properties, which kind of correlate really well with each other. So what that means is if a state has been using rapid chloride test for specification, then if you're using surface resistivity, you have to use a different number. So here is correlation between, again, surface resistivity and rapid chloride. This is data from our Mobile Concrete Technology Center. This is data from, I believe, 11 different states. All of this is field data. This is data from Louisiana. They've done extensive testing as well. And as you could see in their case too, they have a really good correlation between surface resistivity and rapid chloride. Now, what you would notice is in the previous graph, it's just this one, the line is straight, and then the other one, it's not, because in this graph, it's plotted on a log scale. So the important thing with resistivity is it's a really good test, a simple test. But the one thing to keep in mind is there are certain aspects or certain factors that actually affect resistivity. So these 4 are those. One is pore solution chemistry, which is basically the cementitious materials that you have in your concrete, your degree of saturation, your testing temperatures, and your curing temperatures. So all of these are critical. So I mean, they do impact them, but these are things that we can control. So it's just a matter of us being cognizant to it. So here is some data that we have collected with our Mobile Concrete Technology Center. We prepared 2 sets of specimens, and then 1 set were cured in a lime water bath by us in our lab, and then another set was given to Michigan DOT, and they cured them in the moisture room. So for the same set of specimens, our numbers are slightly higher than theirs. So the point here is that the way you cure becomes extremely important. So, both of them are good ways to do it. You can lime water bath, cure them, or you can cure them in the moisture room. But the important thing is, whatever you do, it has to be consistent. So if Colorado DOT is using lime water bath, then the contractors also should be using the same thing, and vice versa. So that's one thing to keep in mind. The other way of running this test is the bulk resistivity test. So with the surface resistivity test, we put the 4 probes on the surface. Now, there are some researchers that claim that, well, because we're only measuring the resistivity on the surface, maybe we are not measuring the true permeability of the entire concrete. So to address that issue, the same resistivity, surface resistivity setup can also be used to measure the resistivity of the entire specimen. You just need to change the setup. We'll show that, Josh and Nicola will show that in the next presentation when we're actually demonstrating it live. There is, again, an ASTRO test method for this, for the bulk resistivity as well. It has the same advantages as the surface resistivity test. So the important thing that I would like to kind of mention here is permeability is really important. It's an extremely important aspect. We had a good test, which is a rapid chloride test to measure permeability, but because it's a labor-intensive test, it wasn't done as frequently as it should be in the past. But now that we have this really simple test, easy test, I think we should use them a lot more to assess the quality of the concrete during mix design and during production. So these tests can be used for both quality assurance for mix design, as well as for quality assurance and for quality control. And so it offers a lot of these benefits. So here are a couple of slides on how different states are using this data. So this is from North Carolina DOT. This was from 2019 data, where this is data from one project. They were measuring resistivity at different days. They were shooting for, I believe, around 13 kilo ohm centimeter resistivity. And in their case, for the particular mix that they're using in that project, not all of the specimens reached the desired resistivity value at 56 days. And then here is some data from Iowa DOT. In their case, for their particular mix, they did receive, or their specimens did achieve the resistivity that they're shooting for. So with that in mind, I'll conclude my presentation, and I will transfer it to Angela.
Thanks so much, Jagan. Really appreciate you explaining all of that to us. And then now we can look forward to actually seeing those test procedures in action. So I'd like to introduce a couple of representatives from the FHWA mobile concrete trailer. Josh Breininger is a staff engineer on the FHWA's MCTC. He is the newest member of the team and assists with data analysis and testing. Josh received his BS in concrete industry management from Middle Tennessee State University, and his research interests include extraterrestrial construction and non-destructive testing. So if you have not asked a question yet, I recommend maybe asking about extraterrestrial construction. I don't think we've heard much about that in any seminars I've been in. So, and then we have Nikolai Morari, who's a senior concrete technician on the FHWA's MCTC. He has been working with the trailer since 2007. Nikolai is an ACI certified concrete technician and has tested concrete from field projects in over 40 states. And you may have seen him demonstrate testing in Colorado during his field visit with us in 2018. So welcome, Josh and Nikolai. Thanks for joining us.
Thank you. Hello. My name is Nikolai. I'm going to show you guys one of the devices which doing the surface resistivity testing, and the name is ProSec. And I want to show you the procedure of this device. It has 4 probes, and before every time we do the test, we need to check the calibration of this device. Just give you the meter. It's supposed to be 90 and 12 kilovolts, kilo ohm. And need to take the 4x8 cylinder. And we have a towel. It's a wet towel. It's not soaked. You just need to dry a little bit. You
have to bring it to saturated surface wet.
Yes, wet, yes. And if you use on a metal countertop, or you cannot place just the concrete like this and do the test. You need to have a kind of a plastic or wood block to keep the specimen of no conductivity. And before we do the test, we need to mark the sample and 4 square equal parts. And because we're going to do the test 8 times, 8 readings, and it's better to take them in the same places. And we'll mark them as 0, 90, 180, and 270 degrees. And let's go this one. And again, I'll tell you about this device. This device has, you can take up to 500 readings. It has 2 buttons. This button is you can hold the number. If you're working by yourself and you work with somebody, just can tell somebody to write the number. And this button actually is storing, it's saving the numbers. And you need to have water just to water the probes, around maybe ½ inch of water before starting. Or you just can use the water towel and do the same way. So let's start to do the test. We got one reading, it's 14.5. We got another reading, it's 14.5. We got another reading, it's 15.1. We got another reading, it's 14.4. And we're doing it 8 times and take the average of this number. This is actually, it's an average of the surface resistivity. That's it what I can tell about this device now, and I'll ask George to show you another device, the GeoTech.
Okay, so the GeoTech is actually super easy to use. Inside it has the 4 probes that you see in the ProSec, but they're at 4 different locations, so that when you close this, it completely surrounds the sample at each of those lines that Nikolai mentioned. Now each of these probes, instead of wetting them, you can either put leather pads that they ship with the device, or this conductivity gel. It's so that there's a solid connection for the charge between the sample and the probes. And it's super easy. You just put the sample inside and you line up the lines with the 4 probes. And then you close the device, make sure it's secure. And then on the device over here, you just have to turn it on. The first time you do it, you have to enter a few settings, but then you just hit start and it'll bring up the 8 readings that you need, as well as the average. And just like that, test is done.
Any questions?
That's all we got. That's how easy they are to run.
Well, thanks so much. Appreciate you demonstrating both those tests for us, and coming live to us from the trailer. That's something we wouldn't have had if we were all in a ballroom together. So taking advantage of some of those opportunities. All right, we're jumping into questions. Mike, did you want to lead this, or do you want me to jump in?
You can go ahead, Angela. Looks like there's 2 that came in. Do you see them?
Yes, I sure do. Okay, so our first question is there a specific performance test to address materially related distresses? Oh, sorry, let me start over here. Is there a specific performance test to address materially related distresses in joints, such as calcium oxychloride formation and freeze-thaw durability related to moisture saturation caused by de-icing salts, such as magnesium chloride? This is definitely a concern that we've seen in Colorado, where we've not had, especially where we've not had supplementary cementitious materials used, and we've had some of those issues with calcium oxychloride formation. So Jagan, do you want to talk just a little bit about some of the testing that can be done to determine if a mix is susceptible?
Sure, yeah, I think we can use a low temperature differential scanning calorimeter to determine the potential for oxychloride formation. That's something that we could use it in mix design stage itself to see if we have enough SCMs in our mixture, to see if there's any potential for the oxychloride formation. So that's the test that they could use. And if the if the participant wants to know more about the test, we would be happy to send them any information that they want.
Great. Okay. Thank you. And I've taken note of who asked that question so we can put you in touch with him. And that is something that's also included in some of the CDOT specs that you'll see and likely could be included. I'm not sure if it is right now in some of the local agency specs, but we could see things headed that way too. So any other questions out there? I'm going to ask Josh if nobody else does about extraterrestrial construction. So Josh.
All right. So when I was in college, I graduated last year. I was an honor student, so I had to do a thesis. And I was talking with some friends. I've always loved extraterrestrial, you know, like space type stuff, things like that. So they said, why not put concrete on Mars? And so I looked it up, and Northwestern University, I believe, had already done it using a Mars soil simulant from NASA, but NASA no longer created that soil simulant. So I decided to try to gather all the materials that they made the soil simulant from and then try to recreate it myself. And it was a sulfur concrete rather than a normal concrete. So the bond was just melted sulfur. And so that was what my thesis was on. And I really enjoyed that. And that was probably one of the most interesting research things I've ever done. I've done a couple others, but that was like key. And I was sad to hear, I was just talking with Joggin. I'm in touch with a few of the professors back at Middle Tennessee State University, and they are just now involved with creating designs and ideas and things like that for lunar concrete. A year after I graduated. So I'm gonna see if I can stay in touch with them, learn a little bit more about that. Yeah, that kind of stuff really fascinates me.
That's super interesting. Thanks for sharing with us. That is something I did not know anything about. So appreciate all the insight.
Talk about it in a while. Appreciate it.
Yeah. Any other questions? I don't see anything coming else in. Mike, did you see anything?
Nope, that seems to be it.
Okay, well, if any of you think of questions after the fact, we are more than happy to address those by email or whatever other method is convenient. And please also know that Joggin's offer is, definitely out there, that if you need any assistance as far as the testing equipment loan or just, personalized demonstrations on some of the different equipment that's available through the trailer, they are more than happy to do that.
Thank you, Angela.
Super. Thanks. Thanks, Angela. So in wrapping up, thanks everybody for participating today. I want to say a special thanks to our speakers, to Charles, Sarah, Joggin, Nikolai, and Josh. Thank you for being here and participating in this. I want to say thanks to Angela for hosting and emceeing the event. Great job doing that. And a special thanks to Pamela Weimer, for helping to organize this. She always does an amazing job pulling these things together, and she's the silent voice in the background today, but very involved in making this a success. So thanks everybody. So we've got 2 more sessions for this conference. That'll be Thursday, February 4th will be the next session. And then there's the final session on Thursday, February 11th. Those will also be from 11:30 to 12:45. I want to say a special thanks to our sponsors again, and that's Colorado Barricade, Cutler Repaving, Colorado Ready Mix Concrete Association, and the American Concrete Pavement Association. So a special thank you to them. We have 2 gift card drawings today. Pam was doing those in the background. So those got pulled. Let me pull that up right now. So congratulations to David Gardner with the City of Gunnison. You were selected for the ACPA gift card. So we'll be in touch with you to connect you up with ACPA to have that happen. And then the second award winner was Scott Good with El Paso County. Apologize if I pronounced your last name wrong there, Scott. So you won the CRMCA gift card. So we'll be connecting you as well after this meeting here. So with that, I think that's everything. So thank you, everybody. Have a good rest of your day. Have a good rest of your week. Be healthy, wash your hands, take care, and hopefully we'll see you in about a week. Take care. Thank you.